Make sure this is set up correctly. Notes mode. Every second page. There we go. All right. Make sure that is. Yeah, it is. Okay. Cool. So I have some data from the last biweekly check-in, and it seems that one of the areas that people are feeling a little uncomfortable around is the capstone project and trying to come up with a clear vision for that. And I'm going to spend more time talking about that on Thursday, but I will at least touch on it here. And one of the reasons that the challenge is left open-ended is because it is an opportunity, but it's not an easy opportunity. It's an opportunity for you to pick a topic that maybe you can actually inspire you to build something that you wouldn't ordinarily build. If I just simply gave you a recipe card and said, here, go make this, you're going to go do that. By giving you a space to explore, I'm giving you the opportunity to find something that maybe you actually could care a little bit about. Now, I admit, I'm probably wrong about this, and there are always going to be some percentage of people who are like, I don't have the bandwidth, or I don't have the interest, or this isn't in my skill set, which is fine, and that's one of the reasons why I gave you examples of I think 8 different potential capstone projects. So at least you could go pick up something and say, well, this is close enough. For me, I have to admit, I sit around and work on these things, and I'm constantly bombarded with ideas, with things that I could actually do. I literally saw someone who built an entire infrastructure for just taking their Claude conversations in Claude code and putting them into what is, when you look at it, a cloud configuration. Now, it's just a private cloud. In other words, they've containerized it and are running everything locally. But it literally, on a message-by-message basis, collects these things, puts them into a queue. It actually has a real queue. And the queue is recoverable so that if the processing pipeline goes down, the messages don't get lost. It puts them into a Postgres database. It then adds a Redis front end on top of that, so you've got a caching layer. It puts an entire search mechanism in there. And I'm looking at this and I'm going, oh, and it ended up using MinIO, which is an S3 compatible local storage instance. And I'm like, looking at this and I'm going, this is an entire capstone project in a single package. Doesn't require any other equipment, doesn't require any free tier. You don't have to worry about monetization. You don't have to think about those kinds of things. And that's what I'm saying, is that I look and I see these things all over the time, and I look and I go, how would I do that? How could I build that as something like a capstone project? And so that's what I'm going to suggest that you try to do to inspire yourself to find something interesting. The other thing that I like to try and recommend is, instead of saying, what can I do for a capstone project, just look around and see what's interesting. One of the things that I learned is that when you start searching for something, it makes it difficult to see the things that are there because they're not what you're searching for. And I'll give you a concrete example of this. Have any of you ever heard of the James Webb Space Telescope? Last month, someone actually published a paper. Now, I think it's been circulating for a little while, and it clearly was a couple of years of work to get to this point, observing that something they do with data from the James Webb Space Telescope, and telescopes in general, they're going back and looking at older data as well and finding the same pattern. Does anybody know how astronomical photography actually works? I mean, it turns out it's really noisy. What you see is the pretty pictures in the end. That's after an awful lot of data analysis, which all happen to be cloud computing pipelines, to be honest, at this point. Many of the resources here, even at UBC, for processing that kind of data are in the high-performance computing portion because the data sets are huge. The analysis they're doing is quite sophisticated and quite complicated. One of the things they have to deal with is the fact that there are all sorts of sources of light that obscure the ability to see what's behind them. Now, when you're on the planet, we have the Kepler effect going on right now, which is basically we've got so many satellites in orbit that it's making it very difficult for astronomers to see anything at this point. But when you look at the James Webb Space Telescope, it sits out in a Lagrangian orbit, so it stays equidistant from the sun and the Earth as we all rotate around. So we can always see it. It's always the same distance. It doesn't have to deal with the satellites around Earth. What it has to do is it has to deal with the lights in the sky, the stars of the Milky Way. You don't think of them as being particularly bright, but when you look up in the night sky, and you're not near the city of Vancouver because, of course, the light will drown it out. When you look up into the night sky, what you see are mostly stars that are from the Milky Way. If you want to see stars that are beyond that, and this is what the astrophysicists do, they filter out the lights of the Milky Way. Turns out they filtered out what they thought were the lights of the Milky Way because the lights they were seeing were bright, very bright. So that meant they were close. So they filtered them out. And someone decided to say, instead of looking for what was beyond them, they said, how do I know those lights are in the Milky Way? And they actually took them, and they took the data, and they began to analyze it. Does anyone know how we detect the distance a star is from the Earth?
I think how redshift did the
Right. Redshift is in fact the key word there. So the idea behind a redshift is that when something is moving away from you, the relativity stretches things out. So in fact, the light that gets to you is shifted down into the redder and redder zone. So you see less and less blue. So what they noticed was that these bright lights they thought were stars in the Milky Way, they were way redshifted, but they were still too bright. So they call them platypus galaxies. Somebody decided not to search for what was beyond those stars, but to just simply look and see what was there, and they asked the right question. And sometimes that's the way projects appear as well. Look at your own life, look at the things you're doing, and say, what am I doing that could be done in a cloud setting? What could I build? I want to be a filthy rich entrepreneur. I want to be just like Elon Musk. All right, you don't have to be just like Elon Musk, but I want to build something really cool, something really interesting. Did anybody ever hear of a social media site called Moltbook?
It's a new one?
It's 4 days old. How could you not know about it? My gosh. It only has, as I last checked, which was about 2 hours ago, 1,599,801 members, all of whom are AI. Humans are not allowed. Well, they're not supposed to be allowed. This is the quintessential vibe-coded project, but it is still a cloud project. I looked at it and I said, wow, this guy basically built something using AI that was a complete piece of shit. No security. Security researchers managed to download 1.5 million access tokens because, of course, you register and you get an access token, and that's how the AI talks to the website because the database wasn't secured. So there you go. Want a project? Go build a Moltbook that actually works right. Now, the guy who built Moltbook actually has the deep pockets necessary to be able to pay for the cloud computing resources that were required as this thing did scale up. But that's the other reason why it's an interesting cloud project. Cloud projects have an unusual ability to scale rapidly. So if you are successful, you can handle that success in ways that are much more difficult if you have to physically order computers, install them in your rack, make sure they're configured, and make sure they're running. What problems do you see in your world that could be solved with an app? Somebody was asking about the terms of service, and I realized that in fact I talked about terms of service. I made you look at terms of service. The dark patterns lab is a really interesting one. Imagine that you were to build a classifier that walked all of these websites and looked for dark patterns. You could actually build a ranking service for who's the sleaziest one on the internet. I know that would be a race to the bottom, but it could be a very interesting kind of project to build. Do you have to actually go and scan every possible website on the face of the planet? There are companies that advertise routinely. I see them in YouTube videos. There are people who routinely advertise the ability to go and cancel services. How many of you have ever signed up for something and then forgotten to cancel it? I mean, this is how gyms survive. People sign up for gym memberships in January because it's part of the New Year's resolution, and then they forget to cancel them until July. Or never. Because, now I'm already close enough to January again, I might as well just keep it. Subscriptions that you once thought were interesting that now you look at and go, wow, they jacked the price up triple. But, of course, it was on auto-renew. That's a business. That's a cloud computing project. That is the kind of thing that you can actually build and say, here's a service that I could build. So look at your life. Look at the things around you. Look at what you do and say, what could I get away with doing? And if you're still out of ideas, find somebody who's got an idea and team up with them. Do some of the heavy lifting. Talk to me. Talk to the TAs. Talk to your AI. Speaking of which, I don't know if it was this class or 416, but somebody apparently said that the peer feedback was AI generated. I haven't investigated that one, but if you give peer feedback that was generated using an AI, I will expect to see it logged in your AI log. Otherwise, you're not actually being honest, because that's what I said. If you use something from AI and it affects the way you think about things, or you use it in something you do, log it. I'm not asking you to justify that. Because what I really want you to do with AI is do what I do. I now have a new pattern with them. They hang up on me. For the last 2 days, I have had conversation after conversation after conversation where they finally just get to a point where they're like, I'm done. I'm like, whoa. Because that's not part of the normal model. It takes a lot of years to get to that point. You too can torture AI. All right, so let's talk about storage. What is storage? Why do we care about it? Storage is important in cloud computing largely because it's the only thing that offers us permanence. Much of what we do is ephemeral in nature. When you build a Lambda, you put a container together. The Lambda and the container are ephemeral. That is, whatever is in them goes away when they finish. So the way that we bridge between persistent and ephemeral is that we build connectors. We connect the ephemeral piece to something persistent. When you build a processing pipeline, let's say you decide that you want to build ML pipelines in the cloud, because everything has to be in the cloud. You spend a tremendous amount of time. I'm gonna back up on that one, because now I won't ask the question because I've already spilled it. You spend a tremendous amount of time when you do things with any large data set moving data around. How many of you have a GPU? Great, it's about half. How many of you know what a GPU is? All right, I saw one person who didn't raise their hand, so I'll go pick on them. So when we process graphics, it's mostly about matrix manipulations, literally math operations where we do transformations of things across them. And we have hardware that optimizes for that, that literally takes matrices and multiplies them together, computes inverses and does that sort of thing. And the reason that people pay lots of money for these things is because they're really good for programming large language models, for example. That's what most GPUs are being used for these days. There's a small contingent of people, deviants though, about half the class, who probably use them for playing video games. Same kind of thing. How many of you have actually studied any video game programming? I know there's a class on it. Pretty cool stuff. Now, they're not really getting down to the nitty-gritty, are they? Teaching you about how you do affine transforms and...
Basic stuff, I think.
Right, so they take one of the engines and show you how to use it. Not how to build the engine, but how to use the engine.
Like OpenGL and stuff? Like.
Wow, are they down at that level? I mean, these days, if you're learning game programming, you're going to be talking about, what, Unity or one of the... There's only a couple.
They made us use OpenGL in that class.
OpenGL? Really? Oh my God, that's like almost as old as I am.
Yeah.
Holy shit. I remember when Microsoft got that running on Windows NT, and that was probably before any of you were born. So they were so proud of it because one of OpenGL's big things was that it could draw teapots. And you're like, teapots? Really? Seriously? Yeah, it turns out that at the time, drawing realistic-looking teapots was quite difficult because of the curved surfaces. And now we do ray tracing. And actually, OpenGL is a ray tracing package, isn't it? We do reflections off of water and other reflective surfaces. It's really pretty amazing what we can do with graphics these days. But most of our GPUs are currently being used to run inference for LLMs or train LLMs. I mean, for a mere $4,000 US, probably more on the actual market, but the price was $4,000. You can buy the NVIDIA 96 gigabyte GPU box that's used for inference and training large language models. I literally just read an article yesterday, day before yesterday, about using the NVIDIA DGX box to fine-tune GPT OSS 70, I think it was. Maybe it was 120. One of the open weight, they're not open source, open weight models from OpenAI. All right, so what we're going to talk about is options in storage. And this is actually a big deal because picking storage is this interesting balance between what am I using it for, how available do I want it, and how much am I willing to pay for it. Because the cheap stuff, there's always some very, very cheap tier of storage, is generally slow. And when I say slow, I don't mean on the order of seconds. I can mean on the order of half a day. So, why would I pick S3 versus using an actual database? Well, at this point, S3 has turned into something that's pretty close to a database. Sort of an interesting growth to watch S3 go from an eventually consistent key value store to being a strong consistency key value store. But you're still not going to take S3 over Postgres if what you really need is a high-performance SQL database with good indexing behavior and strong search. So why is Glacier so cheap? Glacier's cheap because it's slow. I mean, it's literally like, hey, look, we're going to put this in DNA storage. How many of you know that there is actually DNA storage? It turns out the information density of DNA is extraordinarily high, but DNA is very fragile. And it's still not in production use, but people have actually built entire storage systems on top of DNA. So literally stuff floating around in liquids that encode information. How many of you have studied information theory? How many of you have ever used a zip archive? So we've got one person who's... You studied everything, haven't you?
I did like an info, the science course.
Oh, cool. And they talked about Shannon and information theory?
Yeah.
Cool. Excellent. How many of you have ever used a compressed file or a file compression program or anything that makes data smaller? How many of you ever watched a video online? She won't raise her hand for anything. There we go. I got her. Oh, okay, she finally did it. She said, yeah, I've watched a video online once, but it'll never happen again, I promise. all that relies on information theory because all of it relies upon data compression. Now, when you get into data compression, there's two kinds of data compression. One is lossy data compression. We are not generally talking about lossy data compression here because we want to get the whole thing back. None of these examples are lossy data compression. Lossless data compression is what we're interested in. What lossless data compression does, it tries to squeeze out entropy. You know, it's like water in a sponge. We just try to squeeze it out so we don't get any extra water in that sponge. And then we let it sit on the counter for a couple of days and it smells bad and we throw it away anyway. But the point here is that the amount of information in a unit of storage isn't fixed. That's the idea behind information theory, is that, and Shannon's work is really, really amazing. It goes far probably beyond what you actually studied, but it reflects inherent limitations in the universe we have. Oh my gosh, this is getting really cosmic. Okay, well, let's get this back down and grounded, which is you can waste an awful lot of space saying very little. I do that all the time. What is DynamoDB, and how does it differ from Postgres? And the best part is when you actually go to Amazon, has anybody ever used DynamoDB? What's the difference between Dynamo and DynamoDB? What? They both are there. Which one are you going to use? These aren't actually, I'm asking these questions because these are the kinds of design decisions you have to make when you're sitting down designing your cloud computing products, your projects. So we're going to break storage down into 4 categories. Blobs, where here's just a big thing of storage. Most people don't use this, but they can. File storage, which is a traditional hierarchically structured namespace, although I suppose in theory you come up with some sort of clever non-hierarchical structure. God knows, I've worked on those kinds of projects. Object storage. Object storage is a really big one. Object storage is typically something that is retrieved based on a name. Another word for this is often key value store. And then there are databases. And databases are probably the oldest. Well, I have to say they're the second oldest because we have block storage before we had databases. But databases were originally built on top of block storage. People didn't just use block storage. Here's an unformatted, completely blank blob of storage. You've got 20 megabytes. Ooh, so much. I think the largest, I think it was 5 meg. I remember working with a PDP 1123 that had these big storage units. It was about the size of a washing machine. And you literally could take the cartridge out of the top and you could put a different cartridge in, and it was like 5 megabytes. We don't even make USB sticks in 5 megabyte sizes anymore. Block storage, no structure. Here you go, have a nice day, do whatever you want with it. There's a certain freedom in that. You might actually find that's useful for some particular project that you're building. So for example, maybe you want to have your very own custom data format for training your large language models. Most of the time, block storage is used as a fundamental way of managing the underlying physical storage. Sometimes what we will do is we will build logical storage on top of physical storage. So for example, we will actually do what's called erasure coding. Erasure coding is this idea that I want to have copies of the data so that if something goes wrong with one copy, I can still recover the data. And the simplest kind of erasure coding is, I'll just keep 2 copies. But when we start doing that, it becomes more and more cost prohibitive because I might want to keep 3 copies or 4 copies or 5 copies, because if I just keep 2 copies, what happens if they're both in the same rack and the rack goes down? So now I put another copy over in a different rack. Well, now I've got rack to rack copy, but now I've got 3 of them. And then I want it in a different data center, and now I've got rack across an internet. And suddenly this starts to become more expensive. And so somebody said, you know what we could actually do is instead of just simply making complete copies of this, what we can do is we can use information theory to inform the way that we write the data out so that losing any one copy doesn't cause us to lose access to the data. And the earliest versions of this were you could take as few as 3 disks, put them together, and use one of the disks for parity and the other 2 disks as the data. So if any one of the 3 disks failed, you could reconstruct the data from the other 2. It turns out you can scale this. You can actually do 5 disks that gives you 4 disks worth of data, and so on and so forth. And so this kind of very simple scaling provided us with very robust block storage. This still happens in data centers. It still is there underneath. You could, in theory, build this. If you're working in a data center, you could easily be working on XStore, which is the Azure product for this. And XStore is there, and it's doing this under the covers. You don't even get to see it. You don't even know what's going on because it's handling all of this kind of erasure coding. Across data centers, inside of data centers, you name it. File storage, I'm not going to go into great detail because there's like almost everyone is sitting here with a device in front of them, and therefore everybody knows that there's a file system underneath there doing something. And mostly it's just plumbing, and you don't really notice it until it's clogged up and not working right. Sort of like the toilet. And then you fix it and then you forget about it. Object stores are interesting because they are storage that's addressed using some sort of object. That could be a key value store. Key value stores are, in essence, object stores. They're not fixed-sized objects, they're variable-sized objects. It's the address that we use to go and get the object. Sometimes the storage people build block storage that's in fact an object store. So for instance, if I'm storing things in fixed-size blocks, let's say I'm storing them in, I don't know, let's say 4 megabyte blocks. Pick a random number. And I address each 4 megabyte block using a SHA-256 hash of it. So how many bytes is a SHA-256 hash? I love math in the afternoon. Okay, go figure it out. You can use that SHA-256 address as your value in an object store. So now we do have, see, I blended the two. I've got fixed size storage units, but I'm using a hash to access that storage unit. Now the interesting thing about SHA-256 hashes are, we haven't found any collisions yet. So if you already have that in your object store and someone asks to store that or retrieve it again, you don't need 2 copies of it. You can get away with 1. So this became a simple way of deduplicating storage. Clever, right? Why would I use 4 megabytes? Turns out that Dropbox used 4 megabytes. That was their storage unit size. And they use exactly this kind of hashing to keep track of them. Databases. Anybody studied databases? 1 person. 2 people. And of course he studied it because he studied everything. All right. Somebody else in the back. If you've never worked with a database, think of it as, I don't know, what's a good simple analogy for that? Can't use records because no one has records anymore. We don't even have DVDs anymore. No one organizes photos on their phone, so that doesn't really work. We just don't really organize things these days, do we? Maybe you actually have a kitchen with, forks and knives and spoons, and so you have a spot for each one of them. They have a shape, they have a structure, and when you go and you need a fork, you go and you look in the place where the forks are stored. Okay, boy, this is a terrible analogy. Never analogize on the fly. A database takes a piece of information that has some sort of structure and uses that to store the information in what we call a row. Now, each of the elements of the structure are referred to as columns. You can call them other things. I will call them columns. How's that? Because this column row structured database is really, really common. And it has been around for a very long time. And we use it quite frequently when we're building cloud projects. So we make things fast in databases by building these extra data structures on the side called indices. An index, some people call them indexes, but indices are the same thing, just different languages. There's, never mind. So, for example, let's say I have people's names in the database, but I also then have some identifying number for those people in the database. So I can retrieve the record based upon the identifying number, or I can retrieve the record based upon their name. If I don't have an index, the only way I can actually find them is to scan the entire database. But if I have structure to the database, if I have an index, or maybe I'm keeping it sorted by one of the columns, then what I can do is go and I can find things quickly. Indices are used as a means of accelerating the performance of finding data quickly. Guess what? Every app you use, everything you touch with the computer at this point is probably using at least one database. So block storage, raw disks, no file system, bring your own, and they all provide it. Elastic Block Store, persistent disks, Azure Disk, there we go. We just hit the big three. You use them for things like building virtual machine images, anything large and blobby. Hard drive in the cloud, fast, expensive, and attached to a single machine. There we go. You could actually build them to be attached to multiple machines, but that's a trickier problem. File systems, typically they have some sort of structure attached to them. The Elastic File System on Amazon, the file store on Google, Azure Files. This is really here for anything that wants to talk to a file system, that wants that hierarchical structure and complete lack of structure in the files themselves. I mean, you can put anything you want inside of a file here. So the distinction between a file system and a database is that a database structures the stuff you're putting inside of it. A file system doesn't structure the stuff you're putting inside of it. And put whatever you want. It's just a generic but named structured blob of storage. So in theory, you can actually run these inside of a virtual machine and use standard commands you might use on Linux, because everyone's running Linux, right? Except for the deviants amongst you who are running Mount Xinu. How many of you are running Xinu? Since no one's raising their hand, they don't know they're running Xinu. That's even more interesting. Every Mac in here is running Mount Xinu. Probably didn't know that. How many are actually running Linux? How many are running Windows? How many are running Mac OS? A couple people are running on computers but can't be bothered to tell me what they're using. That's fine. Okay. So I always like to note this, that the two of those operating systems were presented at the same conference in the same session in 1973. Now, I'm not talking about the operating system you're running today, but the predecessors of those operating systems. So Unix version 4 and the experimental kernel OS domain architecture were both presented at the Symposium on Operating Systems Principles in 1973, a long time ago. And those are the operating systems we're using today. Unix and Windows. And they both came out of exactly the same kind of lineage. So it's a very narrowly defined community. Linux came along later, but it was just trying to be Unix without all of the licensing hassles. Object stores, flat namespaces for objects. Each objects have some sort of a key, some data, and then we get to put, we've always got to have metadata. Whatever metadata is, you get to define, well, someone gets to define what the metadata is. S3 is a classic example here. Google Cloud Storage, I think it is, and Azure Blob. Use these when you have things that need some key to look them up. So images and videos and documents. These are heavily used behind web pages. So you build a web page, you stick something into AWS, you're putting it into S3, you're pulling it back from S3. These are all built with some sort of content distribution network on the front. There's always a way to cache this stuff so it gets to people faster. When you're sitting at home and you're watching Netflix, Netflix is sitting there streaming things from copies of whatever the video is that are closer to you than Amazon probably is. It's a big hash table. You give it a key, it gives you back a blob. The weird part is like when you look at S3, you're like, but it looks like a hierarchical namespace. They're just strings. It literally is just hashing on the string. There's no actual structure to it. It's very interesting how they construct the image of structure when it's not present. So why is object storage so cheap? I'm paying 2.3 cents a gigabyte in here, and I'm paying 10 cents a gigabyte for Elastic Block Store. This is why it's kind of interesting that S3 is now offering much stronger guarantees. Block storage guarantees are low latency consistent reads and writes. So I write something, I read it back. It's what I wrote. They're providing a much stronger guarantee. Object stores offer immediate consistency, but eventual consistency when you overwrite something. And so that changes your calculus. Now, this is what I was just saying. S3 literally just changed this, like a month ago, 6 weeks ago, 2 months ago, very recently. It's always been this overwrite, it could take a while before everybody learns about it thing. It's low latency, and you use HTTP to talk to it. It's not actually talking to it through a mounted disk interface. So this is still faster. This is slower, but cheaper. You get very available, cheap storage with S3. It's why S3 is still the largest pool of storage that Amazon manages, and it's one of the oldest services they have. I mentioned, I think it's MinIO is what it's called. There is actually an open source package that implements the AWS S3 API. And so you can use that locally for building tests. So it's a time and money trade-off. That's what you're really deciding. When you start designing your cloud projects, what you're really trying to decide is what is important to me. What do I want to optimize for? So here you go, nice little table. I'm not going to read the table to you. It's there. It's in the slides. If you have questions about it, feel free to ask me, but it's too much text on a slide anyway. Good slides have like no words and just pictures. The hidden costs here, and this is often what people don't understand, is anytime you move data out of the cloud, you pay for it. Move it inside of a data center, no problem, free of charge. That's included. That's part of the basic service bundle. The moment it leaves the premises, sorry, we're paying for that because we have to pay an egress charge. We have to pay to use the commercial internet exchange. Those things that you don't even think about when you're sitting at home and you're playing games, or you're talking to people online, or you're, crypto trading on Polymarket. How many of you are paying tuition through Polymarket? How many of you are sitting there looking at Bitcoin drop like a rock right now going, oh, this is hurting? One person, okay, well, he's bleeding. So if you got loose change, you'll probably be taking donations. Is it that bad?
I don't have too much in it.
All right, fine. Fair enough. It'll all go back up anyway. It's just a little more volatile than, I don't know, a GIC. Every operation you do against an API costs money. When you retrieve data from the really cheap Glacier store, it's expensive. It's charged per gigabyte. It's the retrieval price that you're paying, because literally somebody's probably going to some piece of optical media that's extraordinarily slow and physically moving it into a reader so they can retrieve it. This is the kind of place where you put records you're required to keep for a century, but no one's ever going to really access. You put them in something like glacial storage. Moving across regions will cost money as well. So S3 egress to the internet is 0.9 cents per gigabyte. So you put a terabyte up there, it costs you $90 to download it. And remember, you're putting this behind your web pages. So those assets, those things are getting pulled all the time. So you start to see that this adds up. Databases provide more structure than object storage. Object storage is still just a kind of an addressed blob store using a non-hierarchical naming system. It's a key value store. So now what you have is the ability to query things. You build those indices, that's great, that speeds up your queries, but you're still responsible for setting up the indices, by the way. It's not going to happen automatically for you. It's almost always the case that these are used for any kind of complex transactions where you need relationships across them. So we have relational databases, key value stores, Postgres, MySQL, Aurora, Cloud SQL. These have fixed schemas. They often offer strong transactional guarantees. Does anyone know what ACID means? I'm not talking about the street drug. Look it up. You need to know. If you're building cloud apps, did somebody almost flash their hand? I don't know. Peripheral vision thing, sometimes it does that. This is what makes databases useful. That's why you want to know what it actually means. And if I tell you, you won't remember it anyway. If you look it up, you will. And if you don't look it up, then your cloud project will probably suffer when you don't use the right data storage. Key value stores, DynamoDB, Redis, Memcached. These are mostly about caching. These are mostly about things I only read. In theory, you can actually set up, at least Redis, I know, you can set it up to take writes. Bad idea. Never do that. Never use your cache for writes. It's just terrible. Document stores. So document stores are kind of this hybrid between traditional rewritable object stores and databases. So they have characteristics of both. They use some sort of a JSON structure for the data, and then they provide some sort of additional functionality on top of them, so you can do things like index fields. Now, in the case of document stores, you can have fields that aren't necessarily there. When I was in a database, I was thinking rows and columns, but here you can think of it as rows and columns, but the columns are sparse. And you can add a new column just by adding a field to your data structure. There you go. Now you've created a new column. Everybody else is sparse, and this one document you just created has that entry in it. Relational databases are very useful anytime you have multiple discrete things that you're managing or processing that have some sort of relationship. So, for example, when you go to Ticketmaster and you decide you're going to buy tickets to go see, I don't know, anything. Is there anybody else these days who's selling tickets besides Ticketmaster? I know there actually are, but not very many. You have a customer profile. You have a ticket. Those live in different databases. They live in different fields or tables of the same database, perhaps. You don't really know, but somehow you have to coordinate those things. You have to link that ticket to the particular user. When those tickets become electronic, there's yet another database. Now you actually have little wand readers. I've seen this code. Spent a lot of time looking at it. Wand readers, you know those things they read your phone with, your ticket with at the door? Those actually have a copy of the tickets that are authorized, and it doesn't know who you are at that point, but that was all pulled from a larger database and stuffed into that little handset so it can actually register that your ticket was in fact scanned. And they talk to each other because we don't want you scanning your ticket from 3 different entry points at the same time. It's very scammable. And so they have used the technology to build what is fundamentally a vast, very complex cloud computing solution, except that it predates the cloud. Ticketmaster's been around since the late 1980s in some form or another. And some of the code comes from the late 1980s, believe it or not. Consistency here is really important because when I transfer control of tickets from one party to another party, I want to make sure that's done in a consistent fashion. I don't want to end up with the ticket appearing in 2 people's accounts or in no one's account. So that's why those ACID properties I was talking about before become really important. Used extensively in e-commerce, but vertical scaling, i.e. we build bigger machine, fat machine, expensive. At the high end, you can spend $100 million building a huge vertical stack. And there are still people who do that kind of thing because it's necessary for their workloads. But that's rare these days. A lot of what we do is horizontal scaling. Instead of having one very expensive computer, we have lots of cheap computers and we distribute things out amongst them. And then what we're doing is moving data from computer to computer. This is the problem that we talk about in 416, how we do things like horizontal scaling. And it turns out that horizontal scaling is challenging. It's not so challenging if all you're doing is sharing data that doesn't change. But when you start building that machine learning pipeline, who's done machine learning besides him? Anybody? All right, well then I'll ask you. So what happens in machine learning when you're training a model in a neural network? Doesn't matter which NN you want to pick, I don't care.
Yeah.
Let's say it's a 32-layer NN.
Yeah. So like, what do you mean like what happens? Like,
What happens? Where's the data flow when you're training?
you like put into the input layer, it goes like it does a nonlinear transformation in each subsequent layer.
And what are we doing with the data at each of those layers?
We're like clipping it with like a ReLU or something or whatever activation function you're going to use.
We're storing it.
Yeah.
We're storing it. At every point, we're storing it. Now, one of the interesting problems they actually have, because DeepSeek just published a paper on this, one of the interesting problems they actually have is sometimes things go wrong because these are running on large distributed networks, and if one piece fails, you have to build a system that can recover from that failure or start all over again. Literally, like the failure rates are incredibly high. And that's because even when you take the most resilient components and you string them together, small failures end up becoming high probability of failure when you put enough of them together. And I'm going to go back to the opposite end of this, which was block storage. So when you go to Amazon or you go to Microsoft or you go to Google, they will all have a lot of hard disks. I mean, you're probably sitting there going, who uses hard disks these days? Those are like, from ancient history, right along with, printers that worked on stone tablets. You know what the problem with those was? The dust. A lot of dust. Start chiseling out stone tablets. There, I finally got somebody to laugh. I know it's late in the day. It's kind of hard to laugh at these kinds of bad jokes, but I've been using the stone tablet joke for a long time. I still remember listening to this talk. At the time, she was the woman who was the general manager of Amazon Web Services, and she was talking about storage, because she was at the File Systems and Storage Technologies Conference giving a keynote talk. And she said, if you have a drive that has a mean time between failure of 5 years, 5 years, that means that if you have one hard drive, you'll expect to experience one failure in 5 years. Now, let's say that you have, let's see, what is that? 1,700 hard drives. Now your failure rate will be to expect one to fail each day. 365 times 5. And I spitball it at 1,800 and something, whatever. Except they don't buy 1,800 hard drives. They buy thousands of them every day. And they build data centers that use huge numbers of hard drives. And in fact, when you build a rack these days, the racks themselves in a data center are not built to be fixed in place. Haven't been for a while. You put redundancy in there. So if you've got 50 hard drives in there, you use 40 of them and you keep 10 of them for when the others fail, and then you start failing them over, and it literally just happens automatically. It's part of the infrastructure. You don't even know that it's happening, except that somewhere something is monitoring those, and when that last spare fails, a light goes red. You know, kind of like a CCT, right? The light goes red and it says, this has to be replaced. And you know how they replace a rack? They come in with a forklift. And they take a big connector off of it, or maybe multiple big connectors, and they pull it out, and they put a new one in place. And then they take the entire rack off premises, and they tear it down, salvage the parts, rebuild it, and they recycle it back in. This is what you're paying for. Literally the technology that goes in behind here to make sure that you don't have to deal with any of this stuff. It's no big deal. If you've got 50 hard drives, yeah, okay, fine. Maybe you'll get one failure a year. Probably not, right? I think you need 365.25 of them to have one failure a year. So you're not even at one failure a year. Maybe it's one failure a week. You can probably handle one failure a week. It just becomes part of the IT responsibilities. Everything changes at scale. So that's why horizontal scaling ends up being really hard. Horizontal scaling involves building these massive racks that have very high bandwidth across them, but are also fragile. So my point was that machine learning workload, all you need is one component to fail, and suddenly something goes wrong and you have to recover from it. Now you're building a cloud app, you're building a data processing app that has to deal with this kind of thing. You have to think about, how am I going to recover from that kind of failure? When you use key value stores. This is pretty easy. I don't need to have database style joins. I'm not trying to pull things across multiple tables. These are really, I just need something based upon an identifier. That makes it pretty easy. An example of that is that if you're building, how many of you know anything about HTTP? I know that 317 isn't required. He knows everything, right? HTTP? No? 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 Sort of. How many of you ever use a web browser? How many of you know what a cookie is? This is what we're talking about. So when you log in, the problem that we have to solve with HTTP is it is what is called a stateless protocol. There's no connection state. We don't know when you've stopped using it. So what we have to do instead is simulate that. And the way that we simulate that on top of the HTTP protocol is that we send a cookie. And that would imply that it's like tasty, and I think it probably means more that it's just bad for you, because most of the cookies that you get have nothing to do with session state. They have to do with tracking you and figuring out how we can extract even more money from you. But in this case, we are just talking about session state cookies. So you log in, you've authenticated, you get a cookie back. The cookie gets stored in someplace on your file system. And we retrieve that cookie each time for the new request, because that will tell us what session you're a part of. This is what we use key value stores when we're building session space. Now we know what session you are. Document stores tend to be used for things that are database-ish. They have some structure, but they don't need full database functionality. So they're not doing joins. And even that is like, you can do joins across MongoDB instances, for example. There's no referential integrity. If you want the references going back and forth to be maintained properly, you have to do that. You may not have transactional safety. Increasingly, document stores end up, like I said, blending some of the functionality of a traditional relational database with the flexibility of a document store. So if you need to change things, you may have to change it in multiple places. This isn't going to happen automatically. It's not going to propagate through there. So here you go, simple way of keying through this and saying what kind of storage you actually need. Again, you can read the slide, it's there. Misuse of storage will make your life more complicated. How's that? If you use a database as a file system, you can make it work. People have tried to do it. Microsoft crashed and burned in probably Windows Vista, I think. I think they had to pull up the object file system. You can use an object store as a database, and yeah, you can do that, but it's not a good fit. People do it, and maybe that's the right choice for your particular project. So this is what makes this hard, is that we're giving you a set of generic tools, but you're building a specific product. So you need to think about these things and think about how am I going to do this. If everybody in here was doing exactly the same project, you'd all be sitting here going through exactly the same things, and you just would optimize for it by picking all the same, making all the same choices. By having your own project, you get the freedom to explore this and to say, well, you know, that crypto bro thing that what's his name was running, I'm not into that. I don't really want to be out there like fleecing people of their money. What I want to be doing is, I don't know, I want to allow amateur ornithologists the ability to upload photos and compare notes with each other and commune in something that will be interesting. And you're like, whatever. What? Huh? Or I think Waze is the greatest thing that Google ever tried to destroy, and they haven't managed to yet, and so I want to build it again. You know Waze, right?
Waze?
Waze, yeah. It's a navigation app that Google bought like 15 years ago, and they still haven't managed to destroy. It's crowdsourced, actually. It's very interesting. It's a crowdsourced nav app. And Google's taken as much of that technology as they can and put it into Google Maps, but there's still some stuff that they still haven't been able to figure out how to absorb. Or maybe you think that you can outdo Uber Eats or Didi for food delivery. Great, go for it, do it. You probably don't want to necessarily do that if you're really trying to pitch a startup. Find a problem that hasn't been solved yet. That's a much better, more lucrative approach. But the space is the same. You're going to be building something that needs to solve problems that are unique to your particular use. That's why you want to think about not just what are these things, but then how should I not use them? So here's a couple of anti-examples, anti-patterns. choosing what you know because you know it can be okay for a prototype, but often that's a mistake. This is a place where I actually encourage you to use your AI. Don't trust anything it says. It's lying through its teeth. It's not doing it deliberately. It doesn't hate you. It's because, does anybody know what the objective is when they train a large language model?
To just give an answer.
To give an answer. It's actually not quite that bad, but it's close.
I think what it does is it tries to minimize like the cross entropy loss of predicting like the next token.
It tries to give you the most probable response. It says, I've been trained on all the things that people have said across all of these domains, and so I am going to generate a response that has a high likelihood of actually being emitted. I can tell you, if you really want to, you can get them to emit things that are way weird, and they're fun. It's actually a lot of fun, but it's... So you'll notice that one of the things that's not part of this is they're not actually trained to be truthful. It turns out, and this is, I'm being a little more speculative, but this is some of the research I've been doing lately, and there is evidence to support this. It turns out that the reason that you get honest answers back from a large language model has nothing to do with their desire to give you an honest answer. It's because the training data itself represents human interaction patterns, and human interactions tend to be more truthful than not. Now you notice I hedged that a lot. That's the problem. Everything they've been trained on isn't true. All of the interaction patterns they've been trained on aren't necessarily the best ones. They're not even the most honest ones. And then to make matters worse, what they then do is they then give it additional training that says, here are example questions that we have given to, and I'm going to push you here a little bit. Upvoted answers by people in gig workers in low-wage countries. That's the right term, right? So we take answers and we give them to people and we say, thumbs up, thumbs down. I collect these now. I actually have stopped. I won't do it. If you use a large language model enough, has anybody ever received an A/B? Where you get, well, here we go. Here are two possible options. And they want you to rate it. What they're going to do with that rating is they're going to take your response and turn that into training data. My favorite, and I actually have screenshots of at least a couple of these. My favorite is when both answers are wrong. And I'm like, I cannot vote for either one of these because then all I'm doing is a supply chain attack. Very recent paper that actually showed that now that they're using large language models to train on large language model outputs, somebody did that. I think it was an MIT paper actually, and it basically in the extreme, what happens is it just collapses down to the same basic answer, and it's like mush. I mean, humans don't always agree with each other. But in that disagreement, it leaves space for something other than the top survey answer. So here's the reason you have to be careful when you use large language models. And I know this is a bit of a digression from storage, but I'm telling you to use I'm suggesting that using large language models is the reality now. You can't trust them because they're not built to be truthful. They're built to be coherent. And when they take the base model after pre-training, and then they go through and they give it this reinforcement learning with human feedback stuff, and then they do reinforcement learning with verifiable reward, what they do is they train it to become very good at lying. Because what matters most is sounding like you know what you're talking about. Have you ever known anybody who does that? They say something and you go, this is complete bullshit, but they are so persuasive that other people believe them. There we go. We got one person who's actually seen this pattern before. Anybody else? Maybe you're that person. If you're not raising your hand, you've got to be asking yourself that. See, I built a trap for him. You don't have to worry about that. All right. So knowing what you're choosing because of what you know is not necessarily the best choice. Now, since you don't know any of these technologies, and there's so many of them, this is one of the reasons I think you do want to engage with a large language model, because it won't lie to you deliberately, but it still knows a lot. It still basically has been force-fed all of Reddit, which is part of the problem. And it has read everything on Stack Overflow, which is another part of the problem. And it has been trained on all sorts of things that you've probably never even heard of. But if you type platypus galaxies in there, it won't know about them. Do you know why? The paper was published last month. Unless you're using Perplexity, and you can ask Perplexity, it'll actually go and look, and it will find the archive. Actually, it might actually be a journal article now. It's probably an archive preprint. Most things are. It will actually find it, and you can actually read about platypus galaxies. And these are the kinds of things that I do all the time, because I'm crazy. One of the things that really limits the ability in cloud computing is this idea by Eric Brewer that he put together 20 years ago that said that in cloud computing, we get to choose two of the following three properties: consistency, availability, or partition tolerance. So network partitions are really hard to defend against because they're going to happen. Somebody unplugs a cable and boom, you've got a partition. So these are the two that we usually tend to balance out: consistency and availability. You can't have both. People will tell you you can have both, but people will also tell you that this will, this magic cream will put hair on your head or give you some sort of extra superhuman powers. Don't believe them. How many people take vitamins? And yet you can go look at the studies, and most of the studies basically say you're wasting your money. And then you actually start really digging into it, and you find out that most of the things that are sold as vitamins are often not what they're labeled as. And that's when it starts getting scary. Why do people do that? Why do they sell you something and tell you it's good for you? Oh, please. You're not this naive, are you? Right, exactly. When you get that hot person starts talking to you on some social media app, do you immediately think, oh, wow, they're really into me? Or do you start going, what's the scam here? I can't even say it with a straight face, right? It's like, really? Those are all cloud apps. They're all cloud apps, everything. Everything we're talking about here, it all happens on the cloud. So, in practice, Postgres, SQL, consistency, partition avoidance. DynamoDB, availability, partitionability. DynamoDB gives you, in a strong configuration, gives you consistency. But notice you gave up availability. So now, when things are starting to fall apart, you're going to get failures. You're going to get availability failures. Sorry, that service is down. You're going to get a 503 error. Cassandra, which is another database package. Availability and partition ability. So when you start thinking about what you're claiming, you need to think about what does it mean when I just simply say my data is consistent. All right, where's the trade-off here? Because you can't have all three. You can't have consistency, availability. So you don't get to say, I've got 8 nines, and it's always consistent. Because I'm going to look at that, and I'm going to be going, yeah, you're the hot hunk who's like trying to talk to me. No, I'm not going to believe you. And you shouldn't believe yourself when you do that. How many of you have ever lied to yourself? If I eat half a donut, it doesn't count. He's like going, yeah, okay, fine, Everybody's got something like that, right? Yeah, don't lie to yourself. It's not really a good long-term thing. So when you start thinking about data, think about what you're promising when you tell a user that they're going to delete their account. I think I mentioned the whole Facebook thing, right? where Facebook doesn't really delete photos. They mark them, they put them in a blacklist. If somebody asks for this, tell them we don't have it. Okay, great. Nothing could possibly go wrong with that. So delete is not what most people think it is. And you do have to think about this as you build your product. So in delete, you have to wrap this up. Delete for retain for 90 days, blah, blah, blah. So you can come up with all sorts of excuses here. But in the end, you actually have regulatory requirements. So when you start saying we allow, we're GDPR reliant, remember I said that you could have a claim that actually required multiple control points and multiple tests? This is an exact case of that. You make something very broad like that. We are GDPR compliant. GDPR isn't one thing you have to test for and control. It's hundreds of them. How many of you know what the GDPR is? Good. Look it up. So here you go. This is a good example of an actual policy that you can enforce and test and verify is working. You're going to have to make these decisions in your capstone. These are the kinds of questions I want you to be asking. Again, I'm not going to read the slide. It's here. And we're not going to do this today. We're going to do this on Thursday. We're going to actually give you time to talk about and think about and discuss with other people capstone ideas, because it's now time for you to be really seriously moving forward on this, right? I think there's a design thing that was due or is due or something. And the deadlines are there more because I want you to have signposts along the way. They're all there to try and help you make sure that when you are done at the end, you can give me something that I can look at and I can say, you actually learned something out of this class. And instead of feeling like the failure that I probably will feel like when I look at it and I go, great, you vibe coded this on the last day it was due with Coder. Wow. At least he's laughing because he's probably sitting there running Coder right now, right? Yeah, it's not bad, right? It's free. But it ain't Opus 4.5 either. Yeah. Right now, Opus 4.5 is the only thing that's Opus 4.5. Anybody hate Opus 4.5? Please, please. See, I think one of these times I'm going to run a class and I'm going to say that you're going to get credit for disagreeing with me in class. It'll be like an extra credit activity. But it has to be, well-grounded kind of thing. All right, so on Thursday, we're going to talk about your proposals because I don't think anybody actually will have proposals yet, but hopefully people will be a little bit further along. And I will be actually asking people, what are you going to do? What are you thinking about? How do we get you over that timeline? So push everything you have into your repo, even if it's incomplete, so we can actually look and see. And if you've talked about providers and you've been thinking about storage, put that in there so that we have something to talk about. Otherwise, I will sit here and I will make you watch me talk to Gemini. Yeah, Gemini. Gemini's cut me off twice in the last day. It literally just gets to this point where it's just like, I'm done. We have nothing else to talk about. It's like, whoa. I had Claude actually give me 3 ellipses at the end. I was like, okay, pretty cool. It's fun torturing LLMs. Somebody has to do it. And that's going to be it for today. And is that a salute? Please no.
What do we do about the design content?
It should be in your Git repo, right?
But you just mentioned that we're not doing the capstone until Thursday for that, right?
Yeah, so put it in, put in what you've got now and then keep putting on it. Again, the point was that the deadline isn't like I'm going to go looking for all of this in everybody's. If you want feedback on it, by the way, have people been receiving feedback from TAs yet? Because I had to bust some chops on this. I don't like the fact that there aren't hands from everybody going up here. So, because it's really important. If you're not getting that feedback, I have one of the TAs who's not answering me, so I need to follow up with them. And that's making me very unhappy. I have 2 of the 3 who say they're doing this, and they've been asking questions, and I've been giving feedback. So I want to make sure that feedback is getting to you. And if you need feedback and you're not getting it, please reach out to me, let me know. Go to the TA office hours and let them know, hey, I'm not hearing any feedback. Why am I not hearing from you people? I mean, I'm not here because I don't know, why am I here? I'm here because I actually want to help you guys learn this stuff and get something out of it. And at the end, I want you to be able to say, wow, you know, I learned something, like, you know, bad dad jokes. That's fine. At least you learned something. Or I learned not to trust Quencoder or ChatGPT. How many of you have used ChatGPT? How many of you trust ChatGPT? One person. Okay, we need some therapy for you. You know, this is calling for an intervention. All right, so I'll see you guys on Thursday. In the meantime, be safe out there. Yep.
So even after we submit the design pack, are we still welcome to change things like the proposal?
Yeah, of course.
Okay.
Of course. I mean, those are pacing. That's why they're just they're for participation. They're for completion. Those are pacing. You fall a little bit behind. You know you're behind because you're missing those dates. And the more of those dates you see that you're falling behind on, the more you have to basically look yourself in the mirror and go, you know, this is like buying the gym membership and not actually going to the gym.
I see.
Does that make sense?
Yeah, and with the proposal specifically, is that something that we can change like throughout
Yes,
the whole term?
of course.
Like, okay.
Of course. You're not locked into any project that you sign up for. Now, as it gets later and later, it's going to be harder and harder for you just if you decide suddenly, you know, I don't want to do this, I want to do something completely different. That's going to be hard on you, but that's a choice you can make.
And as you make changes, say like any sort of like design decisions,
Document them.
Should we document that just kind of like in the same proposal document, in the same like CC?
As long as you're checking it in so that we have, I mean, I have a history document then, right?
Just as long as like however
Yeah. Yeah. I mean, you guys have already convinced me. I overstructured it as it is. Next time I'm basically going to say, you get to define what your structure is for your project and I will figure it out. Because I think that's the right model. Let me shut off the recording. Somebody's waiting.